All right, and we are back. Well, where we last left off, we made this program, and it basically just takes in an age from the user and prints how many years old you are based off the age you gave. So let's do the exercise that I said that that you guys should try um, last video. So I'm basically just going to take a character. I'm going to start out with basically nothing or a space. I want to take in that character, so enter a character. You picked the character C. And so this is virtually the same thing as the H one. And so I don't feel the need to like super explain it in depth. We have our printf. Uh, and you know what, real quick, I should explain um, real quick like the difference between /n and not. And also, you know what? Because we learned the cool thing about the MSVC, or the CL compiler, Microsoft compiler, how about we just do that? Um, so remember, you go Program Files, go to Microsoft Visual Studio, you go the version that you have, or like the year that you have. It might be 2019, might be 2022, might be 2024, doesn't matter. Community, VC, auxiliary, build, and we want this guy. And we're gonna go like this. And remember, you have to be in CMD. We learned that from last video. You're gonna do a call on this guy, and then I think it's VC bars all.bat x64, which is the architecture. And so now that I have that, I have the CL compiler. And so this is kind of cool because we can start actually debugging programs now. I was going to do this later on, but I think it's cool to understand how things work. And so what I'm actually going to do is I'm going to say that we have an int, apple, or you know what? We have a uh, char name, and the name is going to be John, because why not? Now there's a lot to be said here. This char star, basically, if you know other languages, you can treat this kind of as like string, or however you want to do it. Um, and later on videos, when we get to pointers, I will explain exactly what this means and how it's different as opposed to something like this, which is a character array. In fact, you know what? Let's just do a character array, and I'll introduce you to the idea of arrays. An array is the idea that you have some section in memory. Oh god, this is gonna go terribly. Um, let's get a nice new spot. Basically, in memory, let's say this is my memory, which is like, you could think of it as like RAM. I want to take some subsection of this, and you can think of it kind of like slots. It's a little bit, it's not exactly that, but you can think of it as like slots, or a number of like elements. And so you might have like some data in these slots, and you want to be able to like index into these slots. And so the way we do that is we will say we have numbers. That's what so I'm naming the array, or the variable name, numbers. And I'm saying that numbers has these elements in there. There are 5 elements in here. And whenever you want to um, basically, I'm just going to introduce everything. How about I also introduce the for loop? Is this a good idea? I don't know. Let's just do it. I'm gonna also introduce the for loop. And the for loop has a little bit of a different syntax than you might be used to. No, we'll introduce the for loop in a minute. Let's just show what I wanted to show. I just wanted to show you that there's a little bit of a different syntax here that maybe seems a little bit inconsistent, but when you know what a character array is, um, this basically just means you're doing like J, O, H, and N. And then there's actually a special character at the end here called the null terminator. All C style strings or C strings must have the null terminator. This just inserts it directly, and so you'll see that it says character 5, like a character of 5 length array. And that's a little bit confusing because there's only 4 letters in here, but there's a secret implicit character here at the end that doesn't get added. And so let's just do that. Let's just do that because that's a little bit more intuitive. Nothing is hidden from you. And so what I want to do is I'm going to change this J into a S, son. So yeah, let's do that. So the way we do that is we take the variable name, we index into that type of we index into the like correct slot that we want, and just the thing that's might be a little bit confusing if you don't have you never programmed before is all like arrays and everything like that is all 0 index based. And so instead of saying 1, 2, 3, 4, 5, think of it as 0, 1, 2, 3, 4. But the length is still 5, right? And so what that means is that if you want to get the last character, you're always going to say the the length of this. Let's just do a little like Python here. The length of this minus 1. And so that's how you would get this last character here. But let's just say we want to change the first one. So we want to change the J into an S. Well, very simply, we can just do that like this. And this is like the character syntax as opposed to the double quotes, which is the string syntax. This is not valid. That's not okay. But 1 in here is okay because this is a single character, as opposed to this is a string, which is a many characters or a set of characters. So that's cool. Now, why am I doing this? And is there any point? So let's get to that. Now let's compile. Basically the same type of way that we were doing it before. Instead of GCC, we're going to use CL because that's typically what I use. FE, by the way, as always, you can search up like CL, compiler flags, and whatnot. And they actually have pretty decent documentation. And so I want like output. That's what I want. I did see it. Nope, that's the wrong one. This one. Name an exe file. That's exactly what I want. And so I want this guy, basically. And I'm going to name it YouTube program, like last time. .exe. And I think that's all we should need, maybe. That seemed to have worked. You'll notice here that it actually produced an object file, and that didn't happen with the other one. Technically it did, but it was more like implicit. Object files are the attempt to allow for like parallelization, I guess. It basically makes it so you don't have to fully build everything all at once. You can have like incremental builds, like I can build this file and then I can build another file. And if one file changes but the other one doesn't, then I don't have to build both. That's the idea. I don't know if it worked out entirely in practice. But yeah, there's that. So anyways, devenv. You might have saw me really quickly use this command last time, and you might have wondered, what is this for? Well, if we apply it just before that's interesting, just before an exe, we will basically open up uh, Visual Studio and configure it in a way that lets us debug our program. And so this is Visual Studio. It opened up. It's pretty cool. You press F10 and you'll start stepping. And now you see this is like disassembly. This is kind of weird. Um, is kind of weird. Where is my program? I wasn't actually expecting. Yeah. Shoot. I wonder. Oh, guys, people. What's really important is when you want to debug, you need to include debug symbols. By the way, this is a part of making mistakes. It happens. Just trial and error. That's the only way to do it. But you want to include debug information. And the way you do that is with this flag on CL and MSVC. On GCC, it's going to be probably -G or something like that. And so now we should compile with the correct information that we want. And we can close this down and do it again. Actually, don't think yeah, we probably had to close it down. And so now we can press F10 and we have exactly what we want. Press F10 again. We are on this line. If we type in name, in here there should be a bunch of gobbledygook, right? It's it could be zeroed out, it could not be, but after we go past this line, you can see that this actually has exactly what we put in there, which is kind of cool. And now, when we change this line, we should expect this guy to now be S, which is also pretty cool. So now, yeah, I mean, not much to say about that. Don't worry about this. None of that's important. But basically, that's programming. um, that's once you have these simple primitives, you can build really complex things, like I showed in the first video. And so, real quick, let's use some of the ideas that we learned from the last video to print out what is in here. And so, I already know that this is what I want. But if you didn't, in terms of the format specifier, you would just say printf format specifier, and you would go, this seems to be a good one. And you'd look for probably something like string. And you'd see that, oh, okay, this is a string. And so that's what you'd use to print out. And so this is the original string. This is the modified string. Yep, cool. And so now we should expect that this is going to print the original string John, and then this will print the modified string San, something like that. We'll talk more about the null terminator in future videos, and I'll give you exercises that will make you really think about this null terminator. But for right now, you can disregard it. It has to be there. It's very important to work with a lot of like standard C stuff and like debugger stuff. And that's unfortunate because I think now we realize that length encoded strings are just better, period. Because the way to get the length of a string is you need to count the number of characters until you hit a null terminator. And that can be very expensive if you have really big strings. And it's not even a string, it's just any type of U8. But we'll get into that. Any type of byte, not specifically unsigned byte. But yeah, so there's that. And so let's quickly run this program. Let's compile it first, and then let's run the program. YouTube exe. Yeah, so that's shoot. Why didn't that work? YouTube program exe. Oh, it's probably because I am in CMD and CMD just likes programs like that. Yeah. Okay. Cool. Um, but yeah, so it's basically what we said. It's exactly what we want. Cool. Very cool. I'm gonna look at my notes here. Sorry. Oh yeah, I wanted to explain if you've ever used Java, and I touched upon this a little bit last video. I said that all programs have access to a standard in, um, a standard out, and a standard error. The reason it's important to know these low-level ideas is because you can easily abstract these low-level ideas into the higher-level concepts because that has to be the case. And what I mean by that is that in Java, you will have you'll be introduced to this idea of basically printing, but it'll say something like system.out.println. If you think about this and you know that all programs have access to a standard in, standard out, and standard error, well then the other thing, you don't even have to know this is true. You can just test it and it will work because that's how it has to work that way. There's no other way it could work, right? And so this has this is normally what you do. This is what you're kind of taught. But if you just experiment with the idea and the notions that there's this standard in, standard out, and standard error, then this is also available. And so that's pretty interesting. Um, just I thought that was something I should note. Another thing here. Yeah, okay. So now that I did this, let's talk more about strings. Real quickly, let's go back to this string. And let's go back to John. Actually, I'll keep this, and I'll just say that that is one unit. This is another unit. I also realized that I didn't technically run this, but you can just believe me that this will work for the exercise. I lied to you. Hold on. That will work for the exercise. I'm a serial liar. Hold on. This will work for the exercise. This is perfect. This is what you want. That's what you want. Okay. Anyways, ignore that. This is going to be name2, and it's going to be a string literal. And what that means is, okay, so this is in memory, but it's memory that we own, and it's a part of the stack. And the stack is basically just memory that the program natively gives you, and you can run out of stack memory if you use too much of it. And I guess I can demonstrate that real quick. I can make a int array, just numbers or whatnot. I can make int array, and I can say that we have 124. So that's 124 bytes times 124 times 124. This is a gigabyte. These two are megabyte. This is a gigabyte. And then 124 is going to be a terabyte, probably. And so this should run out of stack memory. I would expect this to mess up big time. This probably actually compiles, but the LSP is confused. And so let's just make that a define, and I guess that segues us into macros, or preprocessor. Preprocessor is the idea of assigning some type of just something. So I will say that this is terabyte. I will say that this is a terabyte, and it's going to basically just take this. Whenever it sees this, it's just going to replace it with the value that it's there. And it's all constant. It happens at compile time, and it's all cool. What is happening? I actually genuinely am unsure why. Is it because it overflows? Sorry guys. Long, long. Is it? It's just too big. It's overflowing. This will probably also stack overflow. Yeah, okay. Total size of an array must not exceed this number of bytes, and basically that's just saying that you used all of the stack um, in a way. There's better, there's a better demonstration that I can do here, but just believe me, that's the case. Um, anyways, what that's supposed to show is that memory is very precious, and that's one of the incentives to do the correct things in these types of scenarios. However, if you need more memory, and a lot of times you will, there is something called heap or heap allocated memory. And we will get into that next video. I'm going to quickly speed up because I don't want to go over too much time here. I don't want to take it too much time. And so we are going to convert this name2 to a string literal. This is Felix. Felix. And let's try to do the same thing. Let's do the original string, print that out. Let's try to change the original string with an S, so it'll be Celix, or Melix. Let's do Melix. Let's try that. And so the people, or the astute among you that already have programming experience will know that this is what we call undefined behavior. Why is it different than this? Because string literals aren't memory that we own. It's not memory that the program owns. It's memory that goes into what we call, I think, the data segment. And the data segment has a lot of interesting properties. And a lot of the time, it will only be read-only. And so I guess that quickly segues into a couple interesting ideas. Operating systems have what we call pages of memory. And these pages have permissions, right? And the permissions look something like this. It's like read, write, execute. And so basically, when you are requesting memory, or when you do something, you're going to get a page back, and it's going to have these specific permissions here. I think the data segment, just based off my foundational knowledge, I don't actually know this, but when you know enough low-level stuff, you can start to make assumptions that are generally correct and like map onto reality, just because it has to work that way. Otherwise, there's no other way for it to work. Um, and so I'm going to assume that this data segment is generally read-only. And so if it tries to write to it, it's going to segfault. And segfaulting is basically just your program crashes. There is a lot more to it, but we're not going to get into it right now. We'll get into it later. This might actually work because it's undefined behavior. But I bet if I do it on the CL compiler, it's not going to work. Yeah, so this works, but it shouldn't, right? And I can demonstrate that. Wrong guy. Jesus. This is annoying. Anyways, this works, but it shouldn't. But what if I said, okay, that's kind of weird. You told me it's not going to work. What if I use GCC instead? And we do the same thing we did last time. You can see. Well, now I compiled it. It's cool. Now let's run it. And it might not actually be immediately obvious, what's going to happen here. So what happened? It seems like we printed out the original string, we printed out the modified string, which is what we would expect from here. And then we started printing out the Felix string, which is the original one from over here. And then we just didn't do anything. What happened? Well, you're gonna have to take my word for it here, but we crashed. We totally crashed. And shoot, sorry, we totally crashed. And it's confusing how or why that happened. I guess I can show a little bit in the debugger a very similar situation here that will demonstrate this. So let's switch back to use CL to compile. And instead of doing this, which will crash, but or which won't crash on CL, we can do something like this. We can say whenever you write, so what when I just talked about the pages of memory and how they have different permissions like read, write, and execute, one that's very consistent um, in having a write protection is the null pointer or the null address. And so if you say 0 and you cast 0, this actually gets us into casting too. So this is good. Casting is the idea of going from one type to the other type. Let's do that real quick. So if I want to say that I'm going to take a, let's think here. How can I demonstrate this? I'm going to take a double, a float. A float is basically just a whole number. No, it's just a decimal number. That's all a float is. Float f, and these names are terrible, by the way. And it's going to be something like this. Okay. You don't have to add the f. I think it'll implicitly cast. But implicit casting is like the compiler doing it for you without you having to explicitly cast, which is this type of idea that I'm about to show you. New int I. These are terrible names. But anyways, what would we expect to happen here? I'm assigning a float, a value here, and I'm casting it to an int. Well, what is an int? Int is just a whole number, and so you can kind of think of it that we are like truncating all of this other information out. It's just getting wiped away. So we would expect this to be 1, right? And so we can test that with the information that we know and have. We can test that. Let's comment this out. And actually, you know what? We don't need all this other stuff. It's getting a little bit crowded. Let's delete that. Let's go F. Let's go I. Again, if you didn't know what you wanted to put here, then you should look it up. Fortunately, I think I have a handle on it. This is a float. This is a int. By the way, I will explain to you exactly how this printf works on a very fundamental level when we get to var args. It's a little bit later, and var args is basically variable arguments. For some reason, the way the compiler people did it, this also goes into ABI, so maybe it's not a good idea to explain it right now. But for some reason, when you want to add more arguments here, like different variables and stuff like that, you don't know the number of arguments that you're actually passing. And so printf has a really neat trick, and it's to do with these format specifiers. That's how it knows how many arguments are here. And so I can actually demonstrate that. I can say ff, and I bet the MSVC is going to say, yeah, dude, this is not good. Something like that. Well, it actually has to compile first, so probably save. Yeah, you see it says warning, not enough arguments passed to the format string. Um, and that's because compilers know this information, but for some reason the C language or standard never adopted uh, this implicit knowledge. Um, and it works the same way here. Actually, this would be the better test if I did this. You know what? That worked, but I bet it's going to seg fault. So that's kind of interesting. I just learned. I didn't learn something there, but like I kind of learned something there. Anyways, that's this is doing some weird behavior, undefined for sure. Just take my word for it. But yeah, so let's compile, let's run it, and we have our float and we have our int, and it did kind of like what I said. It's just going to truncate or delete all these numbers after the point. And so that's cool. That's casting. And what if we wanted to cast this to a char? Should work the same idea. Actually, chars are really sneaky and interesting. Let's say that this is 92. And there's a reason I put this to 92. And I think we're about to see that. I'm going to delete this just so it doesn't like have any corruption or anything like that. Okay, so it's not 92. Well, let's look it up. I meant to get into ASCII anyways, so let's look up the ASCII chart. One thing you'll find is that in all of computer science, in all of programming, in all of coding, and everything like that, our world is held up by agreed upon protocols. And one of the protocols that is most pervasive, and you might already know, is the ASCII table. And the ASCII table basically just says, how do I turn a decimal number into a character? And so what we want is, I just wanted the number A. Oh, it's 97. Okay. So make this 97. And let's compile with GCC. It doesn't have to be GCC, it could be CL. And let's go. And so now we have A. And it's obviously not an int, it's a character. But this is gonna maybe blow people's minds, but the way this works is really interesting. Character is not really a thing in memory. I'm not gonna explain that now, but types don't exist in memory. It's just how you interpret them. And so this feels like it shouldn't work, but I would bet it does. And it does. That's a little bit weird and interesting because the type is int. So what is it actually doing? We'll put that off for now, but that's something to think about. Now, I guess I'll do the crash one real quick. Just bear with me, you're probably not going to really understand what's happening here. But basically, we are taking the 0 address, or we're taking 0, we're casting it to an int pointer, so it's now at the 0th 0 pointer or null pointer, and we're going to write something to it. We'll write 0. Let me use my brain here. Yes, you gotta do that, obviously. None of this makes any sense. This is really weird. I just wanted to show a little bit of a, I wanted to show the seg fault in the debugger. Hello. So go here and world. And so I would argue that this right here, when you write to the null pointer, which should be write protected, it should not have the permission from the OS to do that. This is not going to happen. It'll actually terminate our program or decommit the memory in our program, which will crash our program. That's what's actually happening. And it's kind of cool if you like want to learn about it. And you guys probably will learn about it throughout the series. So let's do this. And actually, no, sorry. Let's do the CL one. Make sure that we have our debug info. ZI. Cool. Let's dev env so that we can debug. Guys, I'm like really struggling here um, with my terminal. Yeah, okay, hold on. You actually have to do exe here. All right, so now we have this. Let's press F10 to step through, and F10 again. Um, and then if we press F10, we should see somewhere in the terminal we have a result here. Now, what happens if we press F10 again? Wow, access the access violation right location at the null pointer. Well, that's what the heck does that mean? It's basically what I said before. We're writing to a page of memory that is protected, that is write protected, and in some cases read protected. So yeah, we're trying to write to that location, and that's just not a good time. And so I just wanted to show that. Next thing I want to show real quick is I want to do for loops and conditionals. Conditional is super simple. Um, we are going to take a variable. So we know variables. We're going to take an apple. We're going to say we have 5 apples. And we're going to introduce this new syntax, kind of. It's not very new, but kind of. We're going to say if some condition, so apple equals 5, we are going to run this code. We're going to print f, and we're going to say I have this number of apples. And we're going to add our apple here, our variable here. Else, so if this condition is true, cool, do this, else do this. Actually, I will just quickly introduce this, why not? Else if, and then else, just because it's worth doing. So if apple is greater than, is less than 5, 4, we'll just say 3 actually. So if it's less than 3, then you're going to say I have less than 3 apples. Yep. And then else, I have um, bunch of apples and this many. Okay, so let's test this out. The way this works is you check the first condition, and if that's true, then you go in here and you don't check any other ones. But if this is not true, then you go down and you check this condition, and you go in here if that's true, and you don't do any of the others. And then if everything else fails, you go to this else. This kind of gets into the ideas of scoping. We can do that next video because this is getting long already. But let's quickly run this and see what we should get. Common knowledge says that we assigned it to 5. We're checking if apple equals 5 or equals 5. And so I think we should get this one. But, you know, maybe I'll be surprised. By the looks of it, we did get this one. So that's cool. So how could we get these other ones? Well, let's look at the condition. Apple is less than 3. Well, that means that apple needs to be 2 or less. So let's change it. And how about this, actually? How about we say something interesting? Let's introduce the idea of changing variables after they're assigned. And we've kind of already done that with arrays, but let's do this. This syntax basically just says that we take the apple, we take the value, and we plus plus. So we just add 1 to it, or we increment it. There's also minus minus, which will give us the opposite of that, which means subtract 1. So let's plus plus. So let's follow this code. We start at 2, we plus plus, so apple's at 3. Is apple Is 3 less than 3? Well, no. So we would probably expect to get this one. Yeah, I have a bunch of apples, and it's 3. What if we said, instead, what if we decremented? What if we did minus minus? So let's run through this. We have 2, minus 1 here. Then we have 1. Is 1 less than 3? Yes. So we would expect to get that one. I have less than 3 apples. Very cool. Very cool. So that's conditionals. And then, how about we did a for loop? In the for loop, let's say that we have our apples here. Let's say that we have 0 apples to start. And then we say apples is less than, so this is a condition. Run this loop while apples is less than 5. And then let's say apples plus plus. Sorry, apple plus plus. And so then we're like combining things here. And so basically we start at 0, 0. Sorry, we start at 0. Apples are 0. We run this loop until apples is basically 5. That's what this means. And we increase apples, or we increase apple plus plus. So we say we would never expect to get this one. And the reason is because as soon as this is 5, then it doesn't stop. It doesn't run. That's what I meant. It stops. It doesn't run. And so how could we do that? Well, first let's demonstrate that that is the case. Well, this is why this is a perfect example of why you want the new lines. Let's run. So I have less than 3 apples. I have a bunch of apples. I have a bunch of apples, 4, but we didn't actually get 5. If we wanted to get 5, we could do equals here, and then we can compile and run this again, and we get exactly kind of what we want here. Let's see how long this is getting. Wow, okay, that's already long. So I'll end it off. I'll end it off here. I want you guys to do the simple exercise of taking an array of numbers. So int numbers equals 1, 2, 3. Take this array, and I want you to write a for loop that sums these numbers, sums these nums, sums these numbers. And so your result should be 1 plus 2, so that's 3, plus 3, that's 6. And then you want to print that result. Print the result. Always do your new line, don't forget your new line. Okay. Cool. And just remember, this is the initial value. This is the condition from which it should continue. And then this is basically the increment of the value, or the variable, initial variable. There's better ways to say this, but I think you get the idea. And so the syntax is actually this. And so it's something like this. But yeah, throughout this video, made a couple mistakes, and that's okay. Like I said in the last one, programmers make mistakes. It happens. It's normal. Learning is you're just not learning if you're not making mistakes. So eventually you make enough mistakes where you make a couple less mistakes, and because you'll just learn from the ones you've already made. And at that point, you can start to do some really cool things. I hope you'll join me for the next one. I had a lot of fun this time. Thank you for all the feedback that I got from certain discords and stuff like that. I wish everyone the best and happy coding.